Thank you for attending today's SBCA webinar, Construction Details for Trusses, Part 1. When metal plate connected wood trusses are being considered for specification in a construction of a project, there can be questions about if and or how trusses can be used in certain applications. Trusses are highly adaptable structural framing products, but it can be difficult for a building designer to know how a truss can be designed and used to solve particular framing challenges. To help, SBCA has worked with component manufacturers across the country to gather common truss construction details that they have created and used with their clients, then recreated all of those details in CAD and have made them free for download to building designers through their website. This presentation is intended for all building designers, and in part 1, we will walk through the floor truss details available through that download. And I'll provide some context or commentary on each one of those details. Subsequent presentations, part 2 and part 3, will look at roof truss details, wall assembly details, and hanger details. This is the 5th in a series of webinars aimed at informing building designers, whether they're architects, engineers, or others in the design community, on aspects of the component manufacturing industry. The goal of this series is to provide structural component design guidance, as well as provide perspectives on what today's component manufacturing industry is capable of, and explore how our industry can be an effective partner with building designers in ways that will make their lives easier and or make them heroes in the eyes of their customers. Now, because the audience for any one of these presentations may include design professionals from different disciplines with varying levels of experience and who may work primarily with either single family, multifamily, like commercial, or any combination of that, most of my observations will remain at about the 30,000-foot view. My name is Sean Shields. I'm the Director of Marketing for SBCA. I've been with the association for over 20 years now, and will be bringing to bear my experience talking with component manufacturers across the United States throughout this presentation. My goal with this presentation and all subsequent webinars in this series is to share the industry's best practices and promote the industry's expertise and capabilities. Here's a brief summary of what I will plan to cover in this presentation. I'm going to start by providing a brief overview of SBCA and its role in the component manufacturing industry. I want to do that to give you a sense for the size of the component manufacturing industry, as well as make it clear the role that SBCA plays in the industry. After that, I'll share a little background on where the construction details came from that we'll be going through today, as well as talk a little bit about some floor truss basics that I think are integral to understanding the details that we'll be discussing. Then I'll walk through the floor truss specific details. There are 21 of them, and then provide some context and commentary on each one of them so it's clear what the detail is trying to communicate to both the building designer and also the installer. Finally, I'll end with a discussion on how today's component manufacturer can be a valuable resource to building designers in the building design process. So the Structural Building Components Association, or SBCA, this organization is the premier trade association for the structural building components industry in North America. It has over 40 years of history, and in that time, SBCA has developed an extensive network that enables it to reach the entire length and breadth of this unique part of the construction industry. SBCA has a strong tradition of providing sound engineering and fabrication guidance to its members. These construction details are one aspect of that. And the goal there is to promote their growth and success in the marketplace. However, as the market has matured, and it's matured very quickly just in the last 10 years, SBCA's primary focus has shifted a bit to helping build connections between companies and individuals throughout the industry, whether they're in the same local market are spread across the continent. Those relationships, whether they're between component manufacturers, between manufacturers and the supply chain, or between manufacturers and the building design community, those relationships are built both through face-to-face events, virtual events online, and through digital communication. SBCA's premier face-to-face event is the annual Building Component Manufacturers Conference, or BCMC. This is traditionally held in the fall. We just had our 2024 BCMC in Milwaukee, Wisconsin in early October. BCMC brings in thousands of manufacturers and suppliers together for a week of intense networking, idea sharing, and business transactions. Now, in addition to the BCMC show, SBCA hosts 3 additional face-to-face meetings throughout the year that they call Open Quarterly Meetings, or OQMs. As the name suggests, they're open to anyone. And these meetings are held across the country and offer anyone and everyone a more intimate opportunity to build relationships with some of the largest and most forward-thinking CMs in the industry. Finally, SBCA has developed an extensive suite of tools and resources for today's component manufacturer that range from digital quality management software to an extensive library of online training tools. How large is SBCA's membership? Well, this map provides a scatter plot of the over 1,300 component manufacturing facilities in the United States. Of those 1,300 dots, 907 of them belong to SBCA component manufacturing members. And as you can see, these facilities reach every community in the country, allowing builders to use these products in any project, no matter where that project is located. Now, to give you a sense of scale, SBCA member facilities sold approximately $9.12 billion in product in 2023 out of an estimated total of $9.31 billion. So the reach of SBCA's membership is quite considerable when you consider that. Finally, SBCA is an inclusive organization, and it welcomes anyone and everyone engaged in the light frame construction industry to help them get tied into our extensive network of structural component manufacturers and their supply chain. There's an infinite number of opportunities for individuals to get involved, meet manufacturers, share ideas, solve problems, receive and offer education, and most importantly, build meaningful business relationships that can transform the way anyone approaches their job and positively alter the trajectory of their business. So one of those tools that SBCA has developed are these CAD structural details. Now, component manufacturers have been generating details like the ones we'll go through today for the installation of their products since the industry's inception in the 1950s. With the proliferation of personal computers and software programs like CAD, the production of these details has expanded exponentially. In the late 2000s, SBCA embarked on an endeavor to collect the most common details produced by its members and boil them down into a standardized library of details. The idea initially was to encourage component manufacturers to use these standard details so they would be more consistent throughout the country. However, it was also quickly recognized that these details would be of great benefit to building designers as well, to help them more easily understand how components could be used to solve various framing challenges. In 2016, so 8 years ago, SBCA released an updated version of these details in CAD file formats. And that's what I'll be walking through today, at least those pertaining to floor trusses. Before we get into those details, I want to talk a little bit about some floor truss basics. Just a few quick notes on terminology. As you can see on the screen, in floor truss applications, 2x4 or 2x3 material is typically used with the wider portion of the board resting on the bearing, or what is known as a 4x2 configuration. Now, some of the floor trusses that we're going to discuss today will be considered a bottom chord bearing. In that configuration, the bottom chord is used to transfer forces to the truss bearings. The bottom chord typically carries combined tension and bending stresses. Another floor truss configuration is considered top chord bearing. In this configuration, the top chord of the truss is responsible for transferring forces to the bearings. The top chord then carries the combined tension and bending stresses. Typically, floor trusses have webs arranged in a pattern to maximize triangulation of compression and tension forces that allow the truss to span large distances. There are also perpendicular webs used at bearing locations and at chase openings. Over the bearing locations, these perpendicular webs allow for efficient transfer of forces directly from bearing walls above the truss into the bearing locations below them. For chase openings, these rectangular or square openings allow for easier installation of HVAC mechanicals, plumbing, and electrical infrastructure. Due to this triangulation, the depth of the floor truss was, as well as the strength properties of the wood used in the construction, play a major role in the distance a truss can span. One other really important concept of floor trusses is bearing area. Bearing area is crucial for floor trusses because it determines how effectively the truss can, 1, transfer its load to the supporting wall or beam, 2, prevent crushing of the bearing surface, and 3, ensure the structural integrity of the entire floor system. Now, if the bearing area is too small, the concentrated load coming through the truss at the bearing location can exceed the capacity of the wall, leading to potential structural failure. A larger bearing area spreads the load from the truss more evenly across the supporting member, reducing stress at the contact point and minimizing the risk of crushing. The key here is that truss designers carefully calculate the required bearing area based on the anticipated load of the truss and the strength of the supporting wall material. Even the grade and species of wood used for the bearing surface, both of the truss and the supporting structure, can have an impact on the floor truss's capacity to handle compressive forces. For that reason, most of the details focus on how different floor truss configurations should be designed and installed to maximize available bearing area, and more importantly, use that bearing area as designed. Okay, let's get into the details themselves. Now, I'll be going in chronological order with these details, but I'll point out where there might be some differences that are noted in details that are numerically out of order. So here we are with detail number 1. This detail brings attention to the need to maximize the bearing area by setting the bottom chord of the truss flush with the outside edge of the supporting structure. You'll also notice that a band is required at the top chord to reduce lateral buckling and rotation forces exerted on the truss that are transferred down from the roof through the walls to the floor system. Often, bottom chord bearing trusses like this will be specifically designed with the outside-most parallel web cut short to accommodate the band along the top chord. Now, there are several details that include banding at the top of the truss that we'll look at today to provide this kind of lateral restraint. Though you'll notice the way in which this banding is affixed changes depending on the particular application. I'll also point out that, just so that it's clear, that this is a bottom chord bearing truss. Now, when a floor truss is utilizing an interior bearing, as it is here in number 2, this detail draws attention to the fact that it's important to maximize the bearing area with full contact along the entire surface of the support structure. The perpendicular webs of the truss panel point should be centered over the interior bearing location. This is to ensure both the compression forces at the bottom and the tension forces at the top of the truss are adequately transferred throughout the rest of the truss to the other exterior bearing locations. In detail 3, we look at a top chord bearing truss. With top chord bearing trusses, the goal with this detail is to maximize bearing area of the top chord on the supporting structure. Again, the bearing surface contact between the support structure and the bottom of the top chord is incredibly important. The newest version of the ANSI TPI-1 standard, TPI-1 2022, addresses this for the first time. It makes design provisions for lumber defects like wane that may reduce the total surface contact area between the top chord and the supporting structure. That's how important this bearing surface area is. Now, this detail calls out a maximum of a 1/2 inch gap between the bearing supporting structure and the first perpendicular web of the truss. Now, this is designed as this gap is designed as a construction tolerance. It also conveniently allows for the potential application of gypsum for fire protection, fire separation. Now, when the truss designer is designing a top chord bearing truss, they check for several forces: compression perpendicular to grain, bending, shear, rolling shear, and tension perpendicular to grain. Those checks are dependent on adequate bearing surface contact. So it's critical to maintain the expected bending forces in the top joint and not exceed that 1/2 inch gap. Logically, the larger that gap is, the higher the bending forces in that top joint. For example, a 1 inch gap doubles the bending forces going through that joint. And depending on conditions, even that small change may cause serviceability issues later on in the building's life cycle. Now, I'll say that there are several top chord bearing truss details available in SBCA's CAD details download that I'm going to be walking through here today, but I won't reiterate all that reasoning each time I mention the 1/2 inch gap. I'll just point it out, and you can think back to sort of logically why that 1/2 inch gap maximum is there. So in detail 4, we see double top chord bearing. Additional bearings can be designed to the interior of a floor system to help support a floor truss system mid-span. This lessens the load reactions at the outer bearings and potentially reduces the amount of lumber and the size of the metal connector plates required for the floor trusses themselves. The important part of this detail is to maintain appropriate bearing area. The bearing area is typically the check for the truss designer in this case. They may or may not design the trusses to meet in the middle like this detail outlines, where they butt up against each other. There may just as likely be a designed gap between these two adjoining top chord bearing floor trusses, depending on the size of the support structure and or the required bearing area. Now, sometimes the bearing area may not be large enough, and the truss designer may then design the trusses to be offset, allowing that top chord to extend over the entire surface of the bearing area. Again, there is a maximum of a 1/2 inch gap between the bearing and the first perpendicular web, again as a construction tolerance to leave room for gypsum if needed. Here's detail number 5, which shows an interior pocket bearing. Now, sometimes the truss designer may need or want to increase the allowable bending forces at the support structure. And so they will design a continuous truss with an interior pocket bearing location. So again, this differs a little bit from the previous in that instead of having two separate top chord bearing trusses, you have a continuous top chord bearing truss here. Now, it should be noted that that continuous top chord allows for an increase in allowable bending. But as the detail notes, the bottom chord can be cut out if necessary or required. There may be a situation where, again, you might want to install gypsum because that interior supporting structure is a wall. It's not necessary to cut that out, but it is allowable. Again, you want to maintain that maximum of a 1/2 inch gap between the bearing and the perpendicular on either side to minimize the bending forces transferred into those top chord joints on either side of the supporting structure. In detail 6, we see floor truss strongbacks. Strongbacks are a key element of floor truss performance as they help distribute concentrated loads to adjacent trusses. In effect, strong backs will dampen vibrations and reduce localized deflection typically caused by live loads. As seen in these illustrations, the strong backs can be affixed directly to perpendicular webs of the truss. You can see that in the one to the far right. Or blocking can be affixed to the truss in other locations to provide a perpendicular surface to attach the strong backs to. Again, as it points out, these strong backs should not be attached to the non-perpendicular webs because you don't want that strong back to be oriented in an angled position. It should also be noted that strong backs can provide lateral restraint for the trusses if it's affixed to the top of the truss, as seen in the middle illustration. Detail 7 shows piggybacks. In piggyback situations, these can occur in floor trusses when a designer may seek to maximize the use of an interior support structure that doesn't provide a lot of bearing area. In this particular case, you will have a top chord bearing truss bearing on a bottom chord bearing truss, which is then bearing on the support structure. As you can see in the detail, again, you want to maximize use of the bearing area on the supporting structure for the bottom chord truss, lining up the parallel point, the panel point over the bearing location. You also want to maximize bearing of the top chord truss on the bottom chord bearing truss and maintain that maximum 1/2 inch gap to the perpendicular web of the top chord bearing truss. In detail 8, we see our first example of a cantilevered floor truss. There may be situations where a floor truss is cantilevered over a support structure to achieve some sort of design element. Again, the key to this design is to maximize bearing over the intended perpendicular webs of the truss to adequately transfer both the compression forces at the bottom and the tension forces at the top throughout the rest of the truss. Now, because this truss is cantilevered, the truss will be designed with banding at both the top and the bottom of the truss to provide lateral restraint. We will see a slightly different variation on this detail later on in the presentation, and I'll point that out when we get to those particular details. Another thing I want to point out is that when the truss is cantilevered, you don't need to restrain. When the floor truss isn't cantilevered, you don't need to restrain the bottom chord because the truss is anchored to the bearing location. But when the truss is cantilevered, then you have to provide lateral restraint at the bottom chord because it isn't anchored to the support structure. In detail 9, we see girder truss ledger for top chord bearing trusses. So if one of the floor trusses is tying into a girder truss, it is typical to use a surface-mounted hanger or a strap hanger, which we'll see a detail for later on. But in some cases, the designer may want or need to tie that truss into the girder using a wood ledger. In this detail, the bottom chord truss bears on the bottom ledger. The top ledger provides lateral restraint in this case. You'll also notice that there is blocking attached to the end of the truss that fits between the top and bottom ledgers. This is typically done to provide adequate attachment area between the truss and the ledgers. In detail 10, we see a similar girder truss ledger situation, but this time with a top chord bearing truss. Now, just like in the previous detail, this can be done with a top chord bearing truss. The top chord bearing truss bears on the bottom ledger, which, as we'll look at a comparison next between the two details, this ledger needs to be larger as a result. It should be noted, though, that in this case, the bearing surface for that top chord bearing truss is only 3/4 of an inch. As such, there is no provision for the typical construction tolerance of a 1/2 inch maximum gap. In this application, because the bearing surface is so small, the top chord trusses will typically be a shorter span and will be installed flush to the ledger. So here we see both of them side by side, both with the bottom chord bearing and the top chord bearing trusses. You can see again how the ledger size changes significantly. One additional thing I want to point out is that with either of these details, the designer is relying on 10D nail patterns to transfer the load from the individual trusses to the girder truss. This too places a limit on the span lengths of the individual floor trusses. So again, this isn't typically going to be done if there are large spans between bearing locations, but for shorter applications, this sort of ledger tie-in to a girder truss is possible. Detail 11 shows a drop top chord. And I think this detail illustrates the clear versatility of floor trusses when trying to frame various building design challenges. One benefit of floor trusses is the ability to drop the top chord of a truss to accommodate things like zero-entry showers or exterior egress locations. Now, this detail shows a design option with a continuous framing member over a bearing location, as opposed to using two separate trusses, which might not be possible given limited bearing surface provided by the supporting structure. Similar to other details, it's vital to maximize the bearing location and center the perpendicular webs over the supporting structure. As the top chord drops, the tension forces in the top chord needs to be transferred to the top chord of the portion of the truss with the lower profile. Now, those tension forces are transferred through the middle section of the transition board in the middle between the top chords. If you look at the plan view, it's a little bit more clear how those forces are being transferred between the higher top chord and the bottom chord using that middle section. If that framing wasn't done that way, this truss, because of the tension forces, would want to pull apart along the top chord over the supporting structure. Finally, the top chord is laterally restrained at the drop location, which also provides a defined boundary for the floor sheathing edge. Now, detail 12 is very similar. Again, it points out that floor trusses offer incredible flexibility. In this detail, we see how that drop in floor elevation can be accomplished. Instead of doing it through a drop in the top chord of a continuous truss, floor trusses of different heights can be run perpendicular to one another. In this detail, a bottom chord bearing truss with a shorter profile bears entirely on the limited bearing area of the supporting structure, and the deeper floor trusses then run perpendicular to the supporting structure. To effectively accommodate the drop and to provide lateral restraint to the trusses bearing on the support structure, 3 inches of shims are called out. Again, just like in the previous detail, these shims provide an effective edge for affixing floor sheathing. In detail 13, we see a situation with an angled bottom chord bearing. Yet another example of the versatility of floor trusses is when a building is designed that may require a truss to span a location where either the trusses are angled or the bearing location itself is angled. And this is great because it's a reminder that each floor truss is designed specific to a particular project. And this custom design approach to floor trusses make them ultimately very versatile for any particular project. So if the support structure is angled in relation to the floor trusses, or the floor trusses have to be angled to accommodate an unusual floor design, you would use a detail like this. Either way, the point of the detail is to show how to design and install the truss so that the band affixed to the top cord of this bottom cord bearing truss need to be aligned with this outside support structure. So again, you typically have some sort of sheathing or structure that will run in plane between the banding and the support structure. And you don't want either the banding or the truss itself extending beyond the support then. And when you look at the overhead view, you can get a sense for how that band then runs perpendicular in flush with the supporting structure, and the truss is angled. Now again, the band provides lateral restraint just as it did in the very first detail that we looked at, which is on the right. Another thing to note though then is that the bearing area of the angled truss will be significantly reduced. And this affects sort of the allowable span length of the floor truss in this scenario. So just like we were talking about with the floor trusses that tied in to girder trusses using ledgers, in particularly in top cord bearing applications where that bearing area is only 3/4 of an inch, in this situation, because of that angle, you're reducing significantly the bearing surface area for that truss. And so that will, in most cases, decrease the allowable span length for that truss application. So this is a little bit of an unusual detail, but it shows a situation that would accommodate an opening in the floor for something like stairs. You can use a detail like this to distribute the end load of a truss to two adjoining girder trusses. As you can see in this detail, the bottom block member will carry the load and will need to be sized appropriately depending on the span of that truss and the forces running through it. And the top blocking will provide lateral restraint. One thing to note about this detail is that typically the blocking affixed to the girder trusses, in this detail, they're located on the other side of the carried truss. But if you wanted a cleaner opening in the floor, that blocking can easily be moved to the other side of the girder trusses. Sorry. Okay. Now again, this banding that you see on the left in the number 13 provides lateral restraint, just as it did at the very first detail on the right. Sorry. Okay, so there's that angled top cord bearing truss. And then there's this angled, sorry, that's a bottom cord bearing truss. This is an angled top cord bearing truss detail. And I got a little confused there because it reminds me that a few of these details do feel a little misordered. But going back to that situation where either a support structure is angled in relation to the floor trusses, or the floor trusses are angled to accommodate unusual floor design, this detail addresses how that should be designed if the trusses are top cord bearing. The key here is to ensure adequate bearing area for the top cords again, transferring load to the supporting structure. Again, you're really relying on that top cord, particularly to resist bending forces. And so because you want to minimize that gap to a 1/2 inch at a maximum to, again, minimize those bending forces, but that angle makes that very difficult to do. And so this detail calls out for affixing blocking to the support structure to, again, increase bearing area for that truss and to keep that design tolerance of a 1/2 inch gap maximum between the blocking and the first perpendicular web. Now in this application, it calls out for a 16-inch minimum length of that blocking to provide enough nailing surface for the required number of nails. In detail 16, I've included this detail because it is currently in the CAD download file, but it was originally meant to address how to position a ledger for exterior stairs when the floor trusses run parallel to the exterior wall. However, there have been recent code changes, and there will be several more in the upcoming model code cycle that significantly change how stair supports need to be blocked. So I think in the near future, this detail will likely be removed from the CAD download, or it will be updated to reflect the changes in the building code. In detail 17, again, this underscores the versatility of floor trusses. For some situations, the building design may require a cantilever beyond an internal support, in this case, a pocket beam. The continuous top chord allows for an increase in bending at the support beam. And consistent with some of the past details that we've gone over, the top chord bearing truss has a maximum allowable gap of a 1/2 inch between the support structure and the perpendicular webs on either support of it. But in this cantilevered situation, just like in the cantilever detail that we covered earlier, the ends of the truss need to be laterally restrained both at the top chord to reduce lateral buckling and rotation, and also at the bottom to provide lateral restraint, again, because the end of the truss isn't anchored to a support structure. I also want to point out one other important difference in detail 17 versus detail 5, which we talked about earlier. This is because of the compression forces in the bottom chord due to the cantilever. We talked about in detail 5, with that continuous top chord, the truss extends to another bearing point, and that will minimize or limit the compression forces under the bearing location in the bottom chord. And that allows that bottom chord to be removed. But in detail 17, because of the cantilever, there is no bearing location on one side of that interior pocket beam support. And so you do have compression forces traveling through that bottom chord, even though it's a top chord bearing truss. And so the detail calls out you cannot cut that bottom chord. And this is an important distinction because that can easily be missed in the field. And that's why, details like this can be very valuable to provide to installers so that they're looking for these things. This is detail 18, a girder hanger. And I'll admit that this detail is probably a little misleading. Typically for a solid beam support, a designer would choose to specify a surface-mounted hanger and not a strap hanger like the one shown in the detail. But when there's a girder truss, you have open webs and angled webs, and so a strap hanger like this would be used because those angled webs of the truss don't provide a solid enough face to affix a surface-mounted hanger in a lot of cases. All that being said, the point of this detail is that when using hangers, no matter what their type, the truss needs to be installed flush against the supporting structure, whether it's a beam or an exterior wall. or a girder truss. Now, the key to this cantilever design in number 19 is to maximize bearing over the intended perpendicular webs to adequately transfer both the compression forces at the bottom chord and the tension forces at the top throughout the rest of the truss. Also, because the truss is cantilevered, the truss will be designed with banding at both the top and bottom of the truss to provide lateral restraint. This one is a slight variation from detail 8, which I talked about earlier. In this detail, it calls for more robust restraint of the truss from buckling laterally and/or rotation. So a designer may use a detail like this for having a more significant band at the top of this bottom chord bearing truss. Again, there also needs to still be banding added to the bottom chord to provide lateral restraint because, again, it isn't anchored to a support structure, it's cantilevered. In detail 20, again, we see another slight variation from detail 8 of the cantilevered truss. All of the same conditions that we just went over apply, but in this case, you'll see that blocking is added between the bands. This detail bothers me just a little bit because that additional blocking is very clear in the isometric view at the top, but they didn't include it in the bottom like they should have. So I'll be making that note. This additional blocking that's called out in the detail, at least at the top, assists both with increasing nailing surface for the application of the top and bottom bands. This blocking also creates an additional nailing surface for the application of exterior sheathing and/or siding. Now, again, in some instances, this block wouldn't be required. It all comes down to sometimes local framing preferences. And sometimes it comes down to, again, those rotational or lateral forces may be a little bit stronger. So calling out a little bit more or providing a little bit more nailing surface area is appropriate. And finally, detail 21, at least in the floor truss section, is addresses cutting of a parallel or perpendicular web. This is the last floor truss detail in SBCA's structural details for CAD. It simply shows that that first perpendicular web that we keep on talking about with regard to that half-inch maximum gap is, in most cases, not structurally necessary. It makes it easier to install. Removing a portion of that web can make it easier to install gypsum for fire stoppage. Because these trusses are top chord bearing, you still want to maintain that maximum half-inch gap. And part of that is you're going to keep sections of that perpendicular web as well as portions of that bottom chord. And you keep those portions for a couple of reasons. One is it makes it easier to maintain, know that you're maintaining that half-inch gap. But it also maintains the integrity of that controlling joint at the top chord, which again is carrying a lot of the bending forces of the truss at that location. And extending or keeping a section of that floor or bottom chord of the floor truss provides additional nailing surface for things like sealing gypsum. So those are the 21 floor truss CAD details. And now I just want to spend a few minutes before we conclude talking about the component manufacturing industry. And specifically, I want to talk about why so much investment has been made into this industry just in the last 3 to 5 years, and why it behooves a building designer to become more familiar with details like this and the capabilities of component manufacturers. So, offsite construction didn't become a sexy jargon term overnight. I can say again, I've worked for SBCA for over 20 years, and at least for the last 12 years, I've been attending the International Builders Show put on by the National Association of Home Builders. And during that time, coming out of the downturn in like 2012-ish, builders were seeing their order files beginning to increase, and we're seeing some stability in the marketplace. And they began to talk on the national level about how their association could expend resources to help builders meet this growing demand. And one of the main things they pointed to was a lack of job site labor. And so in those early years, 2012 through I would say like 2015, most of all the discussions really focused on how to invest resources collectively into trade programs, educational institutions, and the like to draw more people back into the trades. And each subsequent year, there were more and more grandiose ideas about how to get this done. But it was very clear after just a few years that that effort was really falling flat. They really were not having any success bringing a huge influx of people back into the industry. For those of you who have been in the industry for a long time, you may recall that prior to the housing downturn in the mid 2000s, when you wanted to ramp up production, you just threw more bodies at it. And this proved not to be the case as we were emerging from the housing downturn. And so, after 15, so in 16 and beyond, builders began talking about what other solutions are there? And it took them a couple of years, but it soon became evident that they were looking at any and all solutions that took labor tasks off the job site and moved them offsite to manufacturing locations and the like to maximize the efficiency of the labor that they did have on site. And the problem is that this labor shortage has continued to prove very sticky. And so because it's been sticky for so many years, that has really drawn a lot of interest and investment dollars into the component manufacturing space. Just in the last 3 to 5 years, we've seen a considerable up-ramp in the amount of funds that have been poured into component manufacturing, both in capabilities and capacity, to meet the growing demand by home builders to find offsite solutions. So, I put a photo of robots up on the screen just to show where the industry is going. This is certainly not mainstream at this point, but along that continuum, there has been a lot of investment in things that have drastically improved the manufacturing process, both from a precision and quality standpoint to just production efficiency. And so some of those things are automated material handling, equipment like linear saws, which are incredibly efficient at using each board as they are fed through the saws. This is a dramatic improvement from past cutting technology. And while linear saws have been around for probably 15 years, at least from a mainstream perspective, their capabilities have increased dramatically just in recent years. There's also automated jigging systems that allow component manufacturers to lay out truss configurations very quickly. They used to all have to be moved manually, and that was a time-consuming process. There's also laser-guided systems which show fabricators exactly where these connector plates need to be placed, where each lumber member is placed to ensure that each joint is as tight as possible. There's even things like automated nailing bridges for wall panels and of course, robotics. Now, all of that investment, again, has been driven by the need of the builder. So when you look at a chart like this is a pretty recent survey of builders asking them, where they're seeing shortages with subcontractors. And you can see the top three job descriptions that they are in most need of, or at least have the greatest shortages are in rough and finished carpenters and framing crews. So again, there's this continued pressure to find offsite solutions for framing to reduce the labor burden on the on-site framer. And again, it's not only the lack of field labor, but it's also the lack of training and the skills of that on-site labor. The ability of today's framer certainly does not match, and I'm not castigating framers in any way, but it certainly does not match the skill level and experience of framers back in the mid-2000s. It is just a drastically different labor pool. And when you add to that this growing environment of growing liability and enforcement, you can see why builders are very motivated to find more offsite solutions and to move more framing tasks offsite. In addition to that, builders and developers are also looking for ways to better control their costs. And one of the easiest ways to do that is to rely on the manufacturing process, which again, because of the level of sophistication in the design process and the advancements in the fabrication process, it really does allow for more just-in-time production and delivery for builders. And it also allows for greater flexibility in the material used. And so when certain materials become hard to source, component manufacturers are better able to adapt to changes in the supply than some other framing methodologies. So it allows builders and developers to control costs. It certainly allows them to reduce construction schedules because, again, a lot of the framing tests that took a long period of time on the job site have been moved offsite and have been automated. And because the components can be delivered just in time, there's an ability to really compact that construction schedule. Again, when builders also look at all the different options available to them, they find that the component manufacturing industry with roof trusses, wall panels, floor trusses, these individual framing elements, can be installed on the job site in a manner that is not drastically different than how they've done in the past. And so they found it to be one of the least disruptive, if not the least disruptive, offsite option available to them. And part of that then makes it one of the easiest for field labor to incorporate because, again, it doesn't drastically change how they go about erecting a building. That's not to say that there isn't a certain level of training and education that needs to go into transitioning a particular framing crew from one framing methodology to another, but it's certainly less disruptive than moving to something like installing modular. And again, going back to this scatter plot of the 1,300 manufacturing locations in the US, it's easy to see why home builders can easily embrace this framing technology because it's available anywhere and they can adopt it today. Now, if you look at this map and you sort of commit it to memory and then compare it to this map, as just one example, you get a good sense for market penetration. So I mentioned at the very beginning that SBCA's bread and butter for many decades was to provide manufacturing guidance and tools for them. But the market has really matured to the point where SBCA and the industry is more outward facing. But you look at this is just roof truss market share by state. The darker the green, the more roof trusses are used versus other framing methodology. And so you can see most of the country is pretty dark green. The light shades, particularly like in Texas and Oklahoma and Louisiana and Arkansas, this accounts for the fact that nationwide roof trusses account for probably about 70% of all roofs framed. But that's because so many roofs are framed in just the state of Texas. So that really brings that number way down. If you took Texas out of the mix, you would see that market share for roof trusses is probably closer to 80%, even 85%. So in conclusion, I want to make the point or reiterate the point that floor trusses are incredibly flexible framing elements. And these can be used in a wide variety of applications to solve specific design challenges. Whether it's simply changing the depth of the floor truss or swapping out the material that the truss is made out of to a material that has a greater strength property, truss designers have almost an unlimited number of variables at their disposal that they can adjust to design floor trusses to meet any particular need a building designer has. As hopefully these 21 details illustrated, different floor truss configurations, support structures, and support locations, as well as bearing conditions, can be accommodated for any project. But in the end, the key for all of this is for the building designer to find and to work with a component manufacturer to explore together the wide range of possibilities that are available in floor trusses and find a solution that works best for their next project. One thing I want to point out is finding a truss manufacturer if you're a building designer is not always an incredibly straightforward process. So if you have listened to this presentation and you are intrigued and want to get in touch with a component manufacturer, my email address is here on the screen. I would really welcome you to reach out to me, and I would be more than happy to get you in touch with a local component manufacturer who can talk to you more about floor trusses and other structural components and how they can be used in a project. For all of you, I want to thank you for attending this webinar. Again, I would love your feedback on how this presentation can be improved for other building designer audiences. So far, I've found that asking questions in this format can be very difficult, but I've had some very, very good conversations and follow-up over these last few weeks and the days after the webinar. So again, my email address is on the screen. If you have any questions at all or would like to have any further conversation with me, please reach out to me by using the email on the screen. You'll also get a follow-up email to this webinar that will ask you for your feedback. I welcome any and all feedback to help improve these presentations in the future. Again, thank you for attending our webinar today. You will also receive a link in a few days to a full recording of this presentation. Feel free to share that with whomever you choose. Thank you and have a good afternoon.